My name is John Cuneo. I'm an AI solutions engineer or global AI evangelist at a large technology company by day. And in my spare time, I make things like the AI infrastructure planner. Now, the workflow of the AI infrastructure planner is something that I've taken thousands of SEs and countless enterprise organizations through, understanding your workload, deciding on a large language model, sizing that model, working through total cost of ownership, and then beginning the process of architecting the final infrastructure solution. So it's all about AI infrastructure planning. Now, let me take you through the AI infrastructure planner as a walkthrough for this actual platform. So here we can actually start with the getting started, where we've got this very video that you're seeing now will be right here in the platform demo. And then just a brief overview of how this actual platform is put together, some of the way we think about sizing and TCO analysis. So all of that is right here in the getting started page. But let's get to some of the interesting things. Here we have the Gen AI sizing calculator module. Now, in this module, we actually have support for multiple use case profiles. So these use case profiles might be for, let's call it a flagship reasoning as an example. Reasoning. There we go. And this may be where we have our large reasoning models, something like DeepSeek R1. Use case 2, this might be your general purpose tool calling model. And this is where we could have something like GPT OSS, and the other one, a small language model expert. And we might have something like Llama 3.2, 3 billion parameters. So support for multiple different models that we're going to be looking at today. Once you have one or more of the use case profiles that you're going to set up, then we can move on to use case configuration. So for each of these profiles, you're going to select your model and the precision in KV cache precisions. We're talking about quantization of the actual parameters and the KV cache used. Now, what's happening in the background here is when you select a model or you input a model from Hugging Face, it is going to go grab that model from Hugging Face and pull in the config JSON that looks how that model is architected. So we're talking the layers, the vocabulary size, hidden size, all of that in order to estimate the total parameters and active parameters. So if we have a dense model like the Llama 70 billion, then it's going to total parameters and active parameters will be the same. And if we have a mixture of experts or sparse models like DeepSeek, then we need to pay close attention to total parameters versus active parameters. So this is going to be a rough estimate that is within, call it 3 to 5% accuracy based on the different architecture. Now, as new architectures roll onto the platform, then these will be updated accordingly. Otherwise, if you're putting in your own models or even you're dropping in your own config JSON manually, then accuracy confidence will vary there. But anywho, you pop in the model, and it's going to tell you how much memory you need for the model weights and how much memory you're going to need per token for KV cache. Then we start looking at the workload requirements. How many concurrent requests are we expecting at any given time? And the input and output tokens for said request. So once you have the concurrent requests, you have the input and output tokens that'll give you the total sequence length per request. Now we have an idea of all the concurrent tokens we're going to need in this system that we could then multiply by the KV cache per token and add to the model weights. And that's going to give you the total memory required for this particular use case profile. And you'll see that down below. For the GPU selection, multiple GPUs are supported here. Right now, all of them are NVIDIA. So all the way up to the Blackwell 300s, as well as the latest RTX Pro and inclusive of for their workstation solutions, the DGX Spark, AKA Digits platform. So you're going to select that number of GPUs per server. It's going to pull the specs for those GPUs. So the flops at the precision you've selected, the memory bandwidth for the high bandwidth memory on the card, and the actual memory capacity. There's a performance estimate selector here. Basically, how we're estimating the overall token throughput that you'll see below has to do with how quickly we can move KV cache from memory to the streaming processors of the GPU and back. All of that's done on that memory bandwidth on card when we're dealing with local to the GPU models. So with that, there's a couple of different methods here. If we're doing conservative, then we're looking at the end sequence length, so the maximum size of the sequence length. If we're looking at a fair, reasonable estimate, then it's going to be that average. So you take that maximum size divided by 2, and now you have the average KV cache amount of data that you're going to be moving for a particular inference. And if you want to get optimistic, then we bump up the GPU efficiency to 95% versus starting out at 70%. So all that is configurable. Once you input the workload requirements and pick your GPU, then we can have your per use case performance. So time to first token, time per output token, the end-to-end inference time, as well as the effective output tokens per second. Number of GPUs required and number of servers required based on GPUs per server, and the total memory required. So all of that is in your results. With multiple use case profiles, you're also going to want to be looking at your aggregate sizing results. So for all of the configured profiles, what are we looking at? Total memory, total GPUs, etc. So all of that is available here, and it gives you a quick breakdown of the entire solution that we're looking at here. And again, you could have multiple different types of GPUs selected for different profiles. Now, the next piece here is we could actually import these results. So we know the model, we know the scale with which we want to deploy this model. How much is this going to cost? Well, this is where we get into TCO analysis. This supports on-premises that we're comparing against either public cloud. So think your hyperscalers, GCP, AWS, and Azure. Right now, we focus on AWS, GCP, and Azure in the future. But do realize that all those 3 players for public cloud are going to be within the ballpark of one another as far as pricing goes. We also have Token SaaS API. So this is your OpenAIs, this is your Bedrock, your Google Vertex, these types of solutions. We could compare those prices as well. But for now, let's look at the public cloud. So what we're going to have here is a full cost breakdown for on-prem as well as cloud cost breakdown. And what's happening here is whenever we select, that's a summary, we have workload presets here. We could select different options to start with. But whenever we select these specific GPUs that are going to be used, it's going to go out and pull the live on-demand pricing from AWS for the appropriate instance that supports that GPU. So H200 is the P5 EN 48X large. The RTX Pro is that G7E. Blackwell 300 is the P6 P300. So it's pulling the live on-demand pricing and using those instances. So let's look at some of the inputs for on-prem. Number of GPU servers is being calculated based on the number of GPUs required, and you could alter the cost per server appropriately. There's also control servers that we're going to want to consider, so things to run things like Slurm or your Kubernetes controllers, run AI, these types of things. Your storage servers, you could also input, as well as your inter-GPU switches. So at this time, we're not looking at the front-end network. We're focused primarily on the back-end network for this AI cluster. We have a support premium that we're going to put on the hardware, as well as a couple of inputs for software. So your data platform software may cost some money, and there's a placeholder for just miscellaneous software you may want to include in the solution. Personnel to run the thing, as well as facilities costs for racks to actually run all of this equipment and power to run all the equipment. On the cloud configuration side, you can select your region for AWS, as well as your pricing model. So are we going to pay full on demand? Probably not. We're going to do reserved, and you can also adjust to this discount up or down if you have a specific enterprise discount plan with AWS. Add the support uplift, and there's also a toggle for SageMaker that's going to be a 15% premium on top of the EC2 instances. We also have storage services that can be configured, as well as the personnel and miscellaneous software tooling as well within AWS. Think like your CloudTrails and whatnot for all your logging and observability solutions that you may want to include in an AWS-based solution. So once you have all of that, you have your comparison for the two solutions. And in this case, it is 13 million for on-prem, 18 million for cloud. You can also compare that token to SaaS-based pricing. So what's going to change here is we go to your cloud configuration. And in this case, we can choose providers between OpenAI, Anthropic, and the others. Maybe we can take a look at Gemini for the different use case profiles. So flagship reasoning, that's going to be something like a GPT 5.2 Pro. Our tool calling model, maybe we look at Bedrock. Maybe we look at what do we want to do here? Trying to pick something reasonable for us. Go to Bedrock and choose a Llama model. So maybe we do a Scout. It's 70 billion. Small language model. This is where we could go to, heck, why not do GPT-5 Mini out of Azure instead of via OpenAI AI directly. So we have these models configured, and as we scroll up, we can see the effective cost per 1 million output tokens. So for the on-prem, we're taking the estimated effective output tokens and using that as the apples to apples comparison of the input and output token pricing for the SaaS providers. How this works in the back end is when we have the effective output, we're also calculating a ratio of the input tokens from that configured input and output on GPU sizing. This is why you had to complete that section before doing an apples to apples comparison with the cloud providers, because the cloud providers, or the SaaS API providers, factor in input and output token pricing. So you could see here, GPT 5.2 Pro is $21 per million output tokens. Bedrock, 72 cents per million output tokens for Llama 3.3, 70 billion. And Azure OpenAI is 25 cents per million output tokens. For the most reasonable comparison, I recommend you have like or similar models. So I just kind of picked random things here. But if you want a true apples to apples, maybe you're running Llama on-prem and you want to compare against Bedrock's Llama implementation on-prem as well. For some of these closed frontier lab models like GPT, Claude from Anthropic, then you might want to just accept the fact that if you're going to run something on premises, you're going to have to compare maybe like a DeepSeek or a Kimi K2.5 or a Llama Maverick or something like that against those other closed source reasoning models. But you have all of that there. One point of order is that there is a cache tier pricing that is 1/10 the cost on input tokens. So we can flip that on, and if the model supports it, then we will see that cost reflected. So 5.2 Pro doesn't support cache pricing, but if we look at the 5 Mini, we've gone down to 3 cents per million input tokens. So all of that is factored in as well. One other point of order, GenAI sizing is available as well, or not GenAI sizing. Vector database sizing is available as well. You can input document size, so the number of gigabytes of documents you want to put into a vector database, or the number of vectors, whichever you happen to have on hand. So this will help you figure out potentially how many of those storage servers you need for a vector database solution, or if you want to load that vector database into GPU memory, when you go to TCO, maybe bump up the number of GPUs required. We do that, we have TCO. Let's look at the facility design. Now you can manually select your racks, do your power implementation, and start adding racks and going from there. Or once you've done TCO, import the configuration. And it's going to tell you based on the power availability and the RUs that you've selected, it will do the import on how many racks you need for the different servers and networking that you've configured. So your network rack, storage rack, and then some compute racks with the different platforms. Note H200, B300 are automatically imported and allocated. Now, obviously, you may want to adjust how this is laid out, and you could do so very easily, drag and drop. You could also add more racks. So if you want to add another rack, boom, you click the add rack button, and now you can do that and continue to organize your own rack layout. So this is going to help with the facilities design and power planning for your solution. Once it is all said and done, there you have the results summary. This result summary is basically a read-only view of everything that was implemented. So there you go. The final bit here, you can also export to PDF. You put in your org name, your project name, and then you hit the generate PDF button, and it's going to generate all of these results in a PDF that you could then share. Final bit here, you can also share your analysis. So there you go. It's going to give you a nice short URL. Thank you to the gentleman that complained that the prior URLs are far too long. You're right. So now we have a short URL that you can use and send off to people. And what this is going to do is basically pre-populate all of the inputs that were configured in your session and then popped in. So all of that is client side. There you go. That was your walkthrough for the AI Infrastructure Planner. Happy planning.